My name is Debin, and this is a collaborative work with my ex-PhD students and postdocs. All right, so let's get into the content immediately. All right, so the motivation of this work is about the application sandboxing on Android. Right, so this one I think is something that most of the audience is familiar with. So basically on the Android device, there could be multiple applications running on its own sandbox. And this sandboxing makes sure that the resource are being isolated or the faults are being isolated. Right? So you can imagine that these two different apps, let's say the Uber app and the Lyft app, right? They are competitors, but one would not be able to gain any information of the other when both apps are running. Right? So this is a fundamental concept in the Android operating system. Right, but the question we're trying to ask or we're trying to challenge is it secure against side channel attacks? So that's what we are working on in this project. Now, there has been a lot of prior work on this. I just very briefly summarize over here. I don't think I've had time to go through the details, right? But basically, there had been previous work working on CPU cache side channels on mobile devices, on ARM CPUs. So we are not the first one working on that. There has been many other work using sensors, using to infer keystrokes or to work on the wireless charging side channels, and many other side channels as well. Now, the one that we are going to focus on in this work is to use the CPU cache as the side channel. So this slide very briefly summarizes what has been done in the prior work. Now, basically, it has been focusing on that third box on the left-hand side over there, which is about the components that are being shared among different applications or different processes. So for example, those are the Android runtime, the shared native libraries, and etc. So these are the shared components. These previous work focus on how these shared components are being loaded into the CPU cache and how one can use CPU cache side channel to find out what are their runtime status. For example, which particular library is being loaded, or at a very fine-grained level, which particular method inside those libraries are being called. Right? So that is what the previous work has been focusing on. Now, when we focus on this particular block that is being shared among all the different processes on the device, a limitation of such a work is that there could be noise. Because these are being shared, all right, so even if we manage to detect that a particular shared library is being loaded, a particular method is being invoked, it could be coming from any of the different apps that are running, any of the different processes that is running on this particular device. So you couldn't tell precisely which app is doing what by using such a method. So that is a big limitation of the existing work. So what we want to do in this particular project is to see, can we target those components at the upper level, right? So at the application level, for example. Now, if we can do that, then we can precisely pinpoint as to which app is doing what in that case. So that will be a lot more resilient against the noise that we discussed just now, right? So that is what we want to do in this project. Now, before I talk about how we actually did it, I have to cover a little bit of the background, right? So the next 3 slides are on this particular background on DICI, so-called the Dynamic Inter-App Component Sharing with Package Context. This is actually discovered in 2020, all right? Now, basically what this particular previous work find out is that Android allows certain components to be shared among different processes. Right? And there is specific code that you can use in your app to load the context of any other victim app that is running on this particular device. Right? So, and many apps on Google Play Store is actually using this. Right? So we did actually a study. We found out many high-profile applications are actually using this mechanism to load the resources of other apps that have been installed on the device. Now, these resources include the code and third-party shared libraries as well, right? So you can use this exactly this particular coding for the purpose of loading the shared libraries of other apps. So this is what has been discovered in previous work. And once you do that, you can actually check your own memory map. This is actually the memory map that we are actually doing. You can see that, hey, we actually managed to load the library of the victim apps into my own physical memory of the attacker application. Right, so that is the existing work. Right, so with this explanation, I hope our main idea of this project is kind of clear. We are trying to we're trying to leverage this particular mechanism called DICI, Dynamic Inter-App Component Sharing, for the purpose of doing CPU cache side channel attack. Right, now, so this is our idea. How do we leverage this mechanism to obtain very fine-grained runtime information of another app? And the idea is very simple, right? So we load the victim app code into the memory, and then use the CPU cache side channel to probe how this code is being loaded and how this code is being executed. With that, we can find out precisely what the other apps are doing. Hey, is this particular method is being called, or is this particular library is being loaded or not? Right, so that is what we're trying to do here. And the impact of this, if we are successful, is that it managed to break the application sandboxing on Android. Remember, just now I gave the example, Uber is not supposed to tell what Lyft is doing right now. But with this particular mechanism, Uber will be able to find out whether Lyft is actually getting a taxi, is actually making a credit card payment, or whatever. Right, so that is what we are trying to do in this particular project. Now, how do we do it? There are 3 phases that we're going to go through on the steps. The first step is to perform the analysis on the victim app. I used the example just now on Uber and Lyft, right? So for example, okay, Uber will have to first of all perform the static analysis on the Lyft app to find out what are the methods that are inside this particular app, and find out the one that we are most interested in, right? So for example, I want to find out when a credit card processing is being called. So that is the static analysis to locate the libraries to find out the specific methods in the victim app. So that is our first step. Second step is to load that particular piece of code into the attacker's memory. And that is done by the code that I shared with you in the earlier slide. Right, very simple, just a few lines of code to load the context, to load the particular libraries. The last step is to perform the actual side channel probing. Right. Thanks for the previous talk. I don't have to go into the details about how we actually do this. It's using the flush and reload mechanism. There are quite a lot of details that we share in the paper about the engineering details here. So for example, we usually pin our attacker app into the little core, and we find out that it's actually giving us a better accuracy. We have a new way of finding out the threshold for the cache hit and cache miss detection. And we also introduce a output voting mechanism so that we can actually scan multiple targets within the same method and use output voting to improve our accuracy of detecting whether that particular method is executing right now. Right, so with that, we can get a very good inferencing result on the fine-grained activity of the libraries and the corresponding methods. All right, let me talk about the evaluation that we have performed. We have done this on many different devices. In the paper, we mainly reported these 2 devices, and these are relatively old devices. And in fact, subsequently, we actually tested on more latest devices. And we found that it actually works on most of the latest devices. And we also tried this out on the latest Android versions as well. Right, so all these have been tested. There are 2 main user studies, 2 main tests that we have performed. The first one is on this navigation app called Organic Maps. Right, and our idea of this particular attack is, okay, can we find out the fine-grained behavior of this organic map, this navigation app, to find out precisely when the vehicle is turning left, turning right. Right. So it's to find out this precise turning point, and with the timing of every single turning point, we can then potentially recover the route that has been taken. right? So this is a pretty classical attack on the Android privacy breakthrough. So with this, again, remember our attacker app does not require any permission. We simply share the resources of the victim app, monitor the methods being executed, and we can find out when exactly these turns are being made. So in the first step, we analyze the victim app. So we find out, okay, there are a number of methods that are critical for this vehicle turning, right? So a particular method is being called whenever the app plays a audio about turn left or turn right, right? A particular app is being called whenever the view on the app is being updated. So we find out all these methods, and we try to use our side channel monitoring mechanism to target these methods inside the victim's code. And this is an experiment that we have done. You can see the horizontal axis is the time, and we can see that using CPU cache side channel, we managed to detect the execution of these methods. And these methods, like 1, 2, 3, 4, 5, all right, indicates when precisely those turns are being made, right? And the last one, we can also detect a navigation ended, meaning that the vehicle has already arrived at the destination. So we can find out all this information. We can also find out when the vehicle is stationary, because there is a particular method that is being called when the view on the app changes. You can imagine when the vehicle is stationary, the view doesn't change, the map doesn't move. So just by monitoring this particular method, we can also tell whether the vehicle is moving or whether it is stationary. Right, so that is one experiment that we managed to do in breaking through this sandboxing example. We did some comparison with existing work as well. There has been some existing work on this reconstructing the routes, and our experiment shows that we managed to detect most of the turns, and we can even reconstruct the entire route based on that information. Right. Let me move on to the second experiment. Right. The second experiment is about inferring keystroke dynamics, right? So here we are targeting a different app called Briar app, all right? In this case, the purpose of the attack is to find out precisely when each keystroke happens, and with the timing of each keystroke, we could potentially recover the keyboard input itself, right? So that is the second test that we do. Very similarly, the first step is to analyze the victim app to find out all those methods are being called when you make any keystroke typing, right? And after that, we do our CPU side channel monitoring again. And in this case, again, the horizontal axis is the time. And we can manage to detect when those methods are being called, it actually reflects every particular keystroke. And we can also find out some specific methods being called when it comes to the ending of a particular word or when the message is being sent out. Right, so all this timing information could help us to recover the actual text being typed. All right, just a quick comparison of our solution compared to previous work. Number one, no permission is needed in our app. Secondly, we are resilient to the noise that I mentioned at the beginning of the talk, because we are monitoring the code of one specific app, not shared code. We also perform experiments on how many targets we can monitor at the same time, and this is the result. And last but not least, this is the responsible disclosure that we have been working with Google. Right? Google has completed the investigation on this and sent us that information that, okay, it is of moderate severity, and we get a bounty of $250 on this. And I think they are working on a potential fix on this particular problem. Right, with that, I will skip the limitation. Please refer to our paper, and I would like to conclude my talk.